Yes. We proved that this intersect Qn plus 1 is anything Qn plus 1.
You mean in Sn?
N plus 1 because this is n plus 1.
I mean dense in Sn?
Yes, it's Sn. Thank you. Thank you for the correction. Dense in Sn. Anything else you can think about here? This is actually already lots of things are showing a corner of the things, of the real mathematics coming on. Do you know anything about an algebraic variety? Let us consider a fine algebraic variety. The fine algebraic variety, simply said, is just a solution set of a set of polynomials, yes. System of polynomial equations. So what we say is that we're saying this. Let us use this half. So let us, because we're talking about affine, so the ground field will consist of R. So let us take F1 to Fn, the polynomials, with coefficients in R of x1 to xn, invariable. Then an algebraic variety, a real affine algebraic variety, and now just like Professor Trump, when his escalator stopped as soon as he stepped on it, and then when he entered the room, the system didn't work, so he went completely free and insulted everyone in the room. Did you not like that? It's really funny. Trump, the President Trump, when he was going to the United Nations General Assembly, he was, as soon as he and his wife, young wife, reached the escalator suddenly stopped. He nearly fell. So he got angry there. And then when he started talking, the system didn't work. And then, so he couldn't use his electronic file. So now he started completely free on his own, which made him insult everyone in the room. And I would really want to keep that as a record, because no president or no country's leader did that in the past. I'm not saying he's good, but this is unique. This action is unique. Real affine variety. It is this word we're defining is a set, geometric set. Let us call it V, which is of dimension n, dimension, let us say n, but n minus 1 is fine. N minus 1, so we use n here. Such that F1, let us call this, all of them just x. F2x. All the way to Fnx. So this says that the common zeros of the common solutions of all these m polynomials with real coefficients of any degree is called a real affine variety. And some real affine variety, such as this one, can be nicely embedded into Euclidean space of one higher dimension, which we call isometric immersion, and for which we can, because it's embedded in Euclidean space, so we can talk about rational points. So determining what is the cardinality of rational points on these, any of these, and whether it is dense or not, is a major question in arithmetic algebraic geometry, not mathematics. Major question. If you solve some of these questions, you might be looking at field net actually. Arithmetic algebra actually. Some of our colleagues do this. And all of this would depend on, because our topic is geometric sets in metric spaces, we are going to deal with metric spaces and mappings between metric spaces fairly thoroughly, and we go to the bottom. We're standing on the firm ground. So the definition of a metric space is this. Did you display the title page? Yeah, that is the thing which I wanted to first display today, but now it's fine. So go to the next page. So a metric space is any non-empty set and a mapping from its Cartesian product of its with itself to the non-negative real numbers, to the set of non-negative real numbers. Many people don't write it that way. I want to make it precise. Many people only write R on the right and then they start saying these axioms. Because if it is R, then what happens if the image is negative? So it doesn't make much unless that the plus infinity is undefined. You all know that. Plus infinity is undefined. The mapping satisfies three conditions, which we call metric space axioms. The number one condition is that any point in the space has distance 0 to itself, and this is the only place where you get distance 0. That is what the axiom 1 says. Axiom 2 is distance from here to there is the same as distance from there to here. Yes. It looks very pretty intuitive and obvious, although we don't really make any reference to reality here because this is just introduced brutally in mathematics. Axioms are never argued.
One question from here. You said in a variety people wants to know about the set of rational quantities, dense or not. Yeah.
Oh, it's cardinality and it's cardinality.
Yeah. So I was thinking about the topology under the usual topology or the Zariski topology.
The topology is actually, in this case, our topology is the Euclidean topology.
Yeah. Okay.
But denseness is denseness has many equivalent definitions, right?
Yeah. So I was thinking because you are asking about varieties, I was thinking maybe.
Yes, because it's isometrically usually. Even you suppose that this variety is immersed in here. Then you have at least two metrics on it. One is the Euclidean metric of this, but actually this space has already at least three major metrics on it. Any